Hi. In this video, we are going to start our geometry section, and basically we'll look at some theory about triangles, and specifically this is about the five centers of a triangle that you must be familiar with. In Olympiad questions, many times you will have questions involving these triangle centers. So we'll look at the basic definitions and some of the important properties that you must know about these triangle centers. So let's begin with the first point, that is the centroid. So what is a centroid? Centroid is basically the point of intersection of the three medians of a triangle. Of the medians of the triangle. Now, medians are basically lines from the vertex to the opposite side's midpoint, right? So some important properties here for a centroid. So I'll just draw a figure which explains what the centroid is basically. A, B, C here, and you draw a line from A to the midpoint of BC, let's say D, which is the midpoint. This is the median from A. Similarly, median from B would be drawn like this to E, and the third median will pass through this point, common point, and will be from C to F basically. So it will be like this. The figure is obviously not very accurate because I'm drawing it by hand, but it will be from C to F, and this is the point that bisects the side AB. Now this point, which is the point of intersection of these three medians, AD, BE, and CF, is known as G, and that is our centroid, right? Now some important theorems regarding centroids are basically the first property is the centroid divides each median. Centroid divides each median in the ratio of 2:1. In the ratio 2:1. So that means that AG by GD is equal to BG by GE is equal to CG is to GF, that is equal to 2:1. So that is the first property. And the second property is the the three triangles, the three triangles formed by the centroid and any two vertices have the same area, have the same area. So which triangles are we talking about here? We are talking about the triangles formed by the centroid and any two vertices. So that means triangles GAB, triangle GBC, and triangle GAC. These all have the same area, and that is obviously 1 by 3 of the triangle ABC's area, right? You can prove this property simply by realizing that this median divides the overall triangle in the ratio of 1:2. So triangle ABD has area of 1 by 2 triangle ABC, and then in triangle ABD, the GBD will be 1 by 3 of ABD. So that is 1 by 6 of ABD. So you I'm not writing the proof right now, but I'm just telling you that triangle GBD area will be 1 by 6 of triangle ABC's area because it is 1 by 3 of triangle ABD's area. Why is it 1 by 3 of triangle ABD's area? Because one vertex is common and both are on the same base, and the base is in the ratio 1:2, right? This is 1 and this is 2. So the area of this triangle BGD is 1/3 of ABD, and ABD was 1/2 of ABC, right? So this becomes 1/6 of ABC. Similarly, this becomes 1/6 of ABC. Therefore, GBC becomes 1/3 of ABC. So this is important to realize. Another important property of a centroid, which we will not prove right now, is this one. It says the centroid is the point in a triangle. Centroid is the point in a triangle such that the sum of squares the sum of squares of its distances to the three vertices to the three vertices is minimum. What does this mean? This means that the centroid is the point such that GA square plus GB square plus GC square is the minimum possible value. So basically, you could have picked any point inside a triangle. I am picking these arbitrary points. Let's say F, let's say P here and Q here. And from P, I could have written PA square plus PB square plus PC square, calculated the distance of P to the three vertices. What this property says is that PA square plus PB square plus PC square is greater than or equal to GA square plus GB square plus GC square. So if you pick your point P as the centroid of the triangle, the value of the distances to the three vertices adds up to the least possible value. We will not prove this right now because the proof involves a little bit of complex numbers. It is best to prove this using complex numbers. So we have not discussed that in our course yet. So once we do that, we'll discuss this proof using complex numbers later. So right now you just have to take it on a faith basis, but we will come to the proof in due course later, right? So these are the three most important properties of a centroid. I hope you have understood the meaning of this point and this very important triangle center, and you should try to remember these properties for a centroid. We'll go to the next one. This is the orthocenter. Orthocenter is basically the point of intersection of the altitudes of a triangle. Of the altitudes of a triangle. So what are these altitudes? These are perpendiculars dropped from each vertex to the opposite side. So A, B, C. And if you drop a perpendicular from here, this is one altitude, and this is another altitude, and this is a third altitude. Now the altitudes also intersect at a point. The proof that they will intersect in a point will be done in the next section when we discuss Cheva's theorem. And from there we can prove that these altitudes are concurrent. So right now we'll just say that these three altitudes will meet at a point called H, and that point H is our orthocenter, right? Now, one thing that we'll see here, the first property of the orthocenter that we need to know is that the distance from orthocenter to the vertex, from orthocenter to the vertex is twice the distance from circumcenter to the opposite side of the vertex. So let me explain this. So basically this is saying that find this distance AH. So we can find AH, but first let's find the distance from circumcenter to the opposite side of the vertex. So I'll draw a different figure which will incorporate all of these points. So let's see. This is my triangle A, B, C, and one altitude is like this. One altitude is like this. And this is my orthocenter. For circumcenter, I will draw my perpendicular bisectors. Perpendicular bisectors of the sides. So this is my circumcenter. Let's say this is O, right? Now, if O is my circumcenter, what is the distance of the circumcenter to the opposite side of the vertex? My vertex, let's label this vertex is what we are talking about, right? So the opposite side of the vertex is BC, right? So first I want to find out the distance of circumcenter to the opposite side of the vertex. So let's find this distance, O to D, okay? And then we'll figure out what is A to H, right? Okay. So O to D distance is simple. You join this and you join this, and these are the circumradii. So this is R and R, and this angle will be A because the overall angle BOC is 2A, since O is the center of the circle, and A angle BAC is the angle on the circumference of a circle. So it will be half of the angle at the center of the circle. So BOC is going to be 2A. So BOD is going to be A. So therefore, we can easily say that this distance is R cos A. I can say that OD is R cos A. So this statement, this property is basically telling us that the distance of the orthocenter to the vertex is twice the distance from circumcenter to the opposite side of the vertex, and we have found this distance is R cos A. So therefore, distance of orthocenter to the vertex AH is equal to 2R cos A. So this is what the property is saying. We can prove this. We can prove this property. Basically, we have to figure out what is AH distance. You can prove this in multiple ways. You can do similar triangles also. Or you can do simply properties of triangles. So if you look at this triangle, right? If you look at triangle ABE, in this triangle AE has length of, this is C cos B. AE is equal to C cos B. Okay. And in triangle HBE, right? In triangle HBE, I know that BE has length of, okay, AE was not C cos B, obviously. AE was C sin B, because C is AB, so AE is C sin B, and BE is C cos B. So if BE is C cos B, and this angle, if you think about it, this angle is 90 minus C. 90 minus C, right? So, and we know BE. So we can say tan of 90 minus C is equal to HE by BE, right? Therefore, HE is equal to BE cot C. And BE cot C will be C cos B cot C. So cos C by sin C, right? So HE is coming out to be C by sin C is 2R because of sine rule, 2R cos B cos C. So what I get is right now HE distance. And if I have HE is 2R cos B cos C, I want to find AH distance. So AH is equal to AE minus HE. So that will be AE will be C sin B minus 2R cos B cos C. And C sin B can be written as 2R sin C sin B minus 2R cos B cos C. Here again I am using sine rule, and now you can take 2R common. So this becomes 2R sin C sin B minus cos C cos B, right? So that is simply minus of cos of B plus C, right? And minus of cos of B plus C is equal to cos of A. So that becomes 2r cos A. So we have proved by simple trigonometry that the distance of AH is 2r cos A, and that is what this property is telling us, right? If you have, if you don't follow the argument, just go back a few minutes in the videos and follow each of these steps. You will be able to figure out, pause the video and try to figure it out. You will get that this AH distance is 2r cos A, and that is what my property was telling us, right? Let's look at the second property for the orthocenter. The second property about orthocenter that we should know is the property called the Euler line property. So basically this says that the circumcenter O, centroid G, and orthocenter H of a triangle are collinear, and this line is called the Euler line. Also, OG is to GH is equal to 1 is to 2. So basically, the circumcenter, centroid, and orthocenter are collinear, so they lie on a single line. And this line is called the Euler line, and the centroid divides the circumcenter and the orthocenter in the ratio of 1 is to 2. So O and G and H are like this. This is orthocenter. This is the orthocenter. This is centroid. And this is circumcenter. And the ratio of this is 1 is to 2. Okay. So these 3 points of a triangle are lying on a single line. They are collinear and the ratio is 1 is to 2. Actually, there is a fourth point on this line, which is called the 9-point center, which is the midpoint of O and H. 9-point center is midpoint of OH. Again, this property, we will not get into the details and the proofs for this. It can be done purely by trigonometry, or it can be done using complex numbers. And I think the complex numbers method is easier. So we will wait for the section when we discuss complex numbers and their geometrical applications. And at that point, we will discuss these properties. But for now, you can try to get a trigonometric proof for these concepts. It is available in standard textbooks. I would recommend reading S.L. Loney's Plane Trigonometry, chapter 15, which is on properties of triangles. In that chapter, we have a discussion of a basic trigonometric proof of these concepts. So you can try reading that yourself. Let's move on for now. Let's go to the circumcenter. As we already probably know that this is the point of intersection of the perpendicular bisectors of the sides of the perpendicular bisectors of the sides of a triangle. Point of intersection of perpendicular bisectors of the sides of a triangle. You need to also realize that the circumcenter is a point that is equidistant from all 3 vertices. That's why it is the center of the circumcircle, right? From the 3 vertices of a triangle. Some simple facts about circumcenter are that the circumcenter of a right angled triangle, is at the midpoint of the hypotenuse. The midpoint of its hypotenuse the circumcenter of a acute triangle is inside, whereas a obtuse triangle, for an acute triangle, circumcenter is inside, while it is outside the triangle for an obtuse triangle. So the reason the circumcenter is the point that is equidistant from the three vertices of a triangle is because when you draw a perpendicular bisector, any point lying on the perpendicular bisector is equidistant from B and C, for example. And if you draw another perpendicular bisector, that any point on this line will be equidistant from A and C. So wherever they meet, wherever they intersect, that point becomes the circumcenter because it was equidistant from A and B and C. And that distance becomes basically R, which is the circumradius of the triangle. So I think most of you are already familiar with it. So I'll not spend too much time on this. Let's move on to the next triangle center that we have to discuss. This is the incenter. It is the point of intersection of the angle bisectors of a triangle. Point of intersection of the three angle bisectors of a triangle. So suppose I have a triangle like this, A, B, and C. If I bisect angle B, I will make a line like this. Let's say this angle is equal to this angle. Similarly, if I bisect angle A and I bisect angle C, this point is known as the incenter. And incenter is special because from incenter, you can drop perpendiculars to each side and the length of the perpendiculars will be different, will be same, right? The length of the perpendiculars from each side will be same. So from the incenter to each side. This is called the in radius of the triangle, and you can draw a circle therefore which touches the three sides of a triangle, and the center of the circle will be the incenter. Basically, incenter becomes the center of this in circle, and this small r becomes the in radius. You have to realize here that the angle bisector line will touch the side at a different point compared to the point where the radius of the incircle touches the side, right? So this point is distinct from this point. So do not confuse the point of tangency of the incircles with the point where the angle bisector cuts the opposite side. Now, first of all, why do you think we can construct the in radius in this way? The idea is pretty simple. Anytime you bisect an angle, a point lying on this is equidistant from the two sides. Why? Because you can simply prove congruent triangles here. Because you can do angle, angle, and 90-degree and this side, right? These two triangles are congruent, so this distance becomes equal to this distance. So when we have drawn this bisector, any point lying on this bisector is equidistant from the side AB and the side BC. And similarly, if you draw another bisector, any point lying on this bisector is equidistant from side AB and side AC. So therefore, wherever those two bisectors intersect, which is the I point, the point I should be equidistant from AB, BC, and CA. So therefore, you can draw perpendiculars of equal length and you can draw a circle which touches this triangle inside, the incircle, right? Let's look at some important properties of the incenter. The first property is quite important. It says if I is incenter of triangle ABC and the line AI intersects the circumcircle at M, then MI is equal to MB is equal to MC. Basically, this is called the in-center X-center lemma. You can find the proof in standard textbooks. I would recommend that you try to prove this yourself. Uh, you can find it in EGMO book. This is the in-center X-center lemma. You will be able to find the proof easily, but I want you to try it yourself. Basically, what it is saying is AI is the line joining in center to the A vertex, and if you extend that line will cut the circumcircle of the triangle somewhere, right? Let's say this was the circumcircle. This point is where M is. The point M is where the line AI extended cuts the circumcircle. Now we have to show that MI, the distance MI, is equal to the distance MB and also the distance MC, right? The proof is a nice geometrical proof. If you don't get it, we'll discuss it in a future video. But for now, try to do this yourself. This is the famous in-center X-center lemma. So that is an important property that when you extend the angle bisector, it cuts the circumcircle at a point M, and MI is equal to MB is equal to MC. The second property is basically talks about the angle BIC, angle CIA, and angle AIB. And these angles are basically 90° plus half angle A, and this will be 90° plus half angle B, and this will be 90° plus half angle C. This is also very basic. So this is an important property. The angle that is made here, is 90° plus half angle. So I'll just draw a different figure here. Let's say we have a figure like this, and I have drawn angle bisectors. This is my in center, this is A, this is B, this is C. And if I join angle bisectors, obviously this is B by 2 and this is C by 2. So this angle here, BIC, is 180 minus B by 2 plus C by 2. And that is 90 minus A by 2. So that becomes 90 plus A by 2. So simple property, it just tells us the angle BIC. Similarly, angle CIA will be 90 plus half B, and angle AIB would be 90 plus half C. And the last property about in centers is this one. It says if I is the in center, and O is the circumcenter, then the distance OI square is equal to capital R square minus 2R small r. So this tells us the distance between the in center and the circumcenter, and OI square comes out as capital R square minus 2R capital and small r. So this is circumradius and in radius product, right? Now this can be done by two ways: power of a point theorem, and also by simple trigonometry. So you should try these proofs yourself too. The last point that I want to cover here is the X center. X center is similar to the in center, but it is the point of intersection of one internal angle bisector and two external angle bisectors. So if my triangle is like this, A, B, C, then this internal angle bisector and these two external angle bisectors meet at a point. So this angle is being bisected, this angle is being bisected, and this angle is also being bisected. These three points will meet at a point called IA, which is the AX center of the triangle. What is special about IA? We can draw a circle now which touches the sides BC, CA and AB, but it is a circle outside the triangle, and this is called the X circle. The X circle touches the three sides, but it touches one side BC and the other two sides extensions, right? So again, this radius will be known as RA, and there are several trigonometric formulas with which we can figure out what RA is. One property that I will leave you with is that if IA is the AX center of triangle ABC, that is tangent to BC, that is tangent to BC, and E and F are the feet of the perpendiculars from IA to the lines AB and AC respectively. Basically, this is E and F. E and this is F, the perpendiculars. Because this is the point of tangency of the X circle with the extended sides. So if E and F are these two, then AE is equal to AF is equal to S, which is semi-perimeter, AB plus BC plus CA by 2. Why is AE and AF equal? They are equal because A is an external point from which two tangents are drawn to the X circle. So the length of two tangents from a single point outside the circle will always be equal. So AE and AF should be equal. You can prove that the length AE and EF is equal to this, which is the semi-perimeter of the triangle ABC. Again, I will not discuss the proof here because it's pretty simple to do. You can do it yourself. The point of this video was to basically discuss the theory that is essential. In the next few videos for this section of geometry, we will discuss some problems which will employ all of these properties. We'll look at some typical Olympiad questions and try to solve them and learn from there how to apply these properties in actual problems. So that's it for this video. I'll see you next time.